This presentation covers our recent work about simultaneous actuation and localization using electromagnetic navigation systems, which was conducted at the Multi-Scale Robotics Lab at ETH Zurich. Electromagnetic actuation systems use current-controlled electromagnets to generate a magnetic field throughout space. This magnetic field can be used to apply torques upon magnetic devices such as catheters or guide wires to steer them with a high level of dexterity in medical applications. This actuation modality holds great potential for minimally invasive surgical procedures. Such a procedure is illustrated in the video and shows an actuation system consisting of 3 electromagnets. The system is used to steer a magnetic catheter during a minimally invasive procedure. The magnetic field is used to steer the catheter in a desired direction, and an advancer unit attached to the catheter is used to push the catheter forward or retract it. The combination of magnetic field guidance and advancement mechanism allows for navigation through the vasculature. When navigating such a magnetic device inside the human body, it is important to know the position and orientation of the device relative to the MNS coordinate system. For this purpose, we introduce a simultaneous magnetic actuation and localization method. This allows for estimating the pose of the device in real time using a single 3-axis magnetic field sensor embedded in the device. The same electromagnets are used for both localization and actuation. Our method divides the magnetic field of the system into a so-called actuation field and a localization field. The actuation field is generated by slowly changing currents in the electromagnets. These currents generate an actuation field which can be used to orient the magnetic device in the vasculature in different directions. In addition to the actuation field, we generate a so-called localization field by superpositioning small, sinusoidally oscillating currents of distinct frequencies on each electromagnet. Both the actuation and the localization field are sensed by the embedded magnetic field sensor. The localization field generates a set of distinct peaks in the discrete Fourier transform of the magnetic field sensor measurements. For a system with 3 electromagnets, this results in 9 unique measurements which uniquely identify both the position and the orientation of the device in the workspace. These measurements are collected in a so-called phasor matrix. To evaluate the proposed localization technique, the phasor matrix was measured in the workspace of an actuation system consisting of 3 electromagnets using a linear positioning stage with an attached field sensor. After this calibration procedure, the localization was tested using a catheter prototype with an embedded sensor and distal magnet. The catheter was placed in a 2D phantom for navigation purposes. The position of the catheter was recorded using an overhead camera which provided the ground truth for the catheter position. The catheter could be advanced or retracted using an advancement mechanism. By applying an actuation field, the catheter could be directed in a desired direction. Together with the advancement mechanism, this allows for navigating the different branches of the flat vasculature model. Catheter localization was performed at a rate of 10 Hz and the mean localization error in this experiment was below 1 mm. The pose of the catheter within the flat model could be estimated with an accuracy of approximately 1 degree. Actuation was achieved using magnetic fields in the order of 8 milletesla. The localization field frequencies for this experiment were chosen between 70 Hz and 110 Hz with amplitudes below 0.1 milletesla. These localization fields resulted in a negligible motion of the catheter prototype. In addition to this experiment, we evaluated the precision and accuracy of our method throughout the workspace. We measure the precision of our method independent of the position estimation rate as well as the magnetic field gradient. These measurements help in generalizing our results to other actuation systems. We also evaluated the accuracy of our method against the applied actuation field for both static and dynamic actuation fields. Our post-estimation algorithm corrects for errors introduced by electromagnet saturation as well as dynamic actuation fields. The influence of dynamic actuation fields is accounted for by estimating the actuation fields in real time using an actuation field compensation method. On the other hand, Electromagnet saturation is accounted for by estimating the localization field in real time using measurements from a reference sensor that is placed near the electromagnets. To summarize our work, we introduced a simultaneous actuation and localization method for electromagnetic actuation systems. The method was tested in a workspace of 8 centimeters and achieved a mean post-estimation accuracy of 1 millimeter and 2 degrees at an estimation rate of 10 Hz. The method is generic and requires a single 3-axis Hall sensor to be embedded in the device. Our future work will be focused on scaling the presented system to a clinically more relevant size. If you want to know more details, you can find our paper under the following link. Thanks for your attention, and we hope you found our presentation interesting.